first model is when the tire is hyperelastic and the surface is rigid. Then I'll be describing the hyperviscoelastic modeling of the tire rolling on a rigid surface. This change in material properties allow you to define the effect of temperature and speed on the contact stresses. Then going back to a hyperelastic tire, but in this case the surface where the tire is rolling is not rigid anymore, but is elastic and deformable. And then the properties for the surface will change to viscoelastic. So we can consider the effect of the temperature and the speed on the pavement. And after that, I will describe the semi-coupled approach to model tire-pavement interaction. And I will conclude my presentation with some final remarks. So first, the American Society of Civil Engineers periodically assessed the infrastructure of the United States. And in 2013, they concluded that $1.7 trillion are needed by 2020 to maintain in good condition the surface transportation system. On top of that, 85 billion of annual investments are needed to improve the condition of the existing assets. And 32% of major roads are in poor or a mediocre condition. This means that, this is becoming more and more common knowledge for everyone, that the pavement infrastructure, the infrastructure in general in the United States is in really poor condition. So how to tackle the problem? How to solve and make a better infrastructure? Specifically for pavements, we need to look at the procedure for the design of pavement structures. So if we want long-lasting pavement design, we need to look at first the actions of the pavement, which are and the materials, the loading, the pavement structure, and environment. Studying all these can improve the design of long-lasting pavements. So the materials, for example, if we're considering recycling materials that can perform better in the field, then pavement structure is just the layer configuration of the pavement, the thicknesses, along with the materials and the structural capacity, the environment, temperature, moisture, freeze and thaw cycles, and loading, which is the focus of my research. And then you have the mechanistic response of those pavements, which will provide you with the deflections, stresses, and strains, and the empirical part, and they're linking to each other, which will tell you the damage that the pavement will experience. And all these are related to each other. Again, the focus of my presentation and in general my research is the loading component of the design analysis and design procedure. Unfortunately, the current design methodology for pavements oversimplifies the effect of the tire. First, it assumes that the load is applied statically, that it doesn't change in position or time. Second, it assumes that the contact stresses are applied only in the vertical direction and they are uniform. Third, it assumes that the contact area between the tire and the pavement are circular. And this assumption is what allows to perform an asymmetric analysis, which is one of the advantages, that they're relatively simple and it doesn't require too much computer power, but it is not an accurate representation of the tire effect. Not only that, this simplification has consequences, not only in the pavement responses, but also in the prediction of damage. And this is a topic that has been researched for quite a long time now. Another consequence of studying the tire pavement interaction is the evaluation of rolling resistance. So LCA is a tool to evaluate the environmental impact of the pavement in general, since the materials until its construction. And these are the 5 phases of the LCA analysis for flexible pavement. So first is material production, then construction, use, maintenance, and end of life. So inside the use phase, we have albedo, leachate, and rolling resistance. And this is where the modeling of the tire pavement interaction becomes important, because we have a series of factors here: the texture of the pavement, the heat exchange between the tire and the pavement, the roughness of the pavement, and the contribution of the pavement structure to the rolling resistance. The model that I developed focused more on the contribution of the pavement structure to the rolling resistance. So based on that, the objective of my research is to predict the tire pavement contact stresses by modeling the tire and the pavement as deformable bodies. As of now, there are models out there that can predict contact stresses between the tire, but it assumes that the surface where the tire is rolling on is rigid. And we're going to improve those models to include the flexibility of the pavement and predict not only the contact stresses, but also to have a study of the rolling resistance phenomenon. So moving on to the experimental program, we did measure the contact stresses between the tire and the pavement for two different tires. First, the wide base and the dual tire assembly. And for each of these two tires, we consider a set of loads and tire inflation pressure that cover a wide range. First, the tire inflation pressure varied between 552 kilopascals to 162, and the load varied between 26.6 kilonewtons up to 80. So that's a range between, this is 125 psi and 552 is around 80 psi, and the load between 6 and 18 kips. This is the measuring system that we use. This machine is operated by the CSIR, and it's composed of two assembly pads that have instrumented pins in the middle section of each pad, and each pin has strain gauges that measure the strain as the tire is rolling over the assembly pads. Each pin and strain gauge in the pins are calibrated to convert these strains in forces, which divided by the coverage area of each of the pins provided with the contact stresses. When we were analyzing the measurements, we noticed that there's an issue with this conversion factor, and it's that in order for that conversion factor to be valid, the pin has to be in full contact with each of the ribs of the tire, which usually doesn't happen all the time. There is a possibility that a pin can be located at the very edge of a rib, which can give some can provide some issues with the readings. As part of the experimental program, the contact area and the deflection, the P delta curves for each of the tires were measured. This will help us for the calibration of the model. So when we do the modeling of the tire, we can compare the contact area that we are measuring with what the finite element is predicting, and the same with the deflection of the tire. So now I'm gonna just describe briefly some results that we got from the experimental program. This is the variation of the maximum vertical contact stresses. So we see that for the dual tire assembly, when the load is high, we don't have a significant effect of the tire inflation pressure, but that is not the case for the wide base tire. We also see that the maximum vertical contact stress is higher for the wide base than for the dual tire assembly under the same load. And those results are summarized in this plot. So the vertical axis is the maximum vertical contact stress for the dual tire assembly, and the horizontal axis is the same value for the wide base tire. And we see that most of the values are below the quality line, meaning that the maximum vertical contact stresses are higher for the wide base tire than for the dual tire assembly. This plot is comparing the magnitude of the in-plane contact stresses, meaning the magnitude in the longitudinal and transverse direction. So the vertical axis is the ratio between the maximum magnitude of the contact load with respect in the transverse direction with respect to the vertical one. And we see that most of the values are between around 0.16 and 0.35, meaning that the bulk of the maximum transverse contact stresses varies between 15% and 35% of the vertical contact stresses. This is becoming a common knowledge in the pavement community that the The transverse contact stresses are important, and this is our measurements are in agreement with that statement. Based on the variation of the contact stresses along the contact length, we were able to develop analytical expressions that can predict the vertical and the transverse. We couldn't get into the variation of the longitudinal contact stresses because the shape of the variation is not uniform first with respect to the location of the rib. So if it's a central rib, the shape of the variation is different than if it's an edge rib. But for the vertical and transverse, this equation was proven to be successful to predict the variation of the vertical and transverse contact stresses along the contact length of the tire. And that is reflected on the coefficient of correlation. We see that the lowest value was close to 0.80 to 0.79, but most of the values are above 0.95, which is an excellent agreement. So now moving on to the tire models. So again, we developed 4 tire models. First, I will be describing the tire geometry and materials because it's what is common for all the models. We model for this phase of the tire modeling, we focus on the wide base tire, and that didn't change. So the geometry and the material characterization for the tire is the same. Then I will briefly describe the kind of finite elements that we use for the finite element modeling, and then I will move on to each of the assumptions for the surface or the pavement. First, when it's fully rigid and the surface is not deforming, and then if it's a deformable body, which is kind of like what we have in the pavement structures. And then for each of those two, we will have, in the case of the rigid surface, we have 2 assumptions for the material properties of the tire. First being hyperelastic, and then hyperviscoelastic, which again allows you to assess the effect of the temperature and speed. In the case of the deformable body or pavement, then the assumption will change for the pavement itself. So first, we will assume that the pavement is, the AC layer of the pavement is linear elastic, which we know is not very accurate, but we decided to do this as an initial step. And then we will consider the pavement as a viscoelastic. And then we were able to consider different temperatures in the pavement structure. So for the tire geometry, once more, we model a wide base tire. We measure the dimensions of the cross section and distribution of the material properties of each of the components in the tire. So we consider 5 components, which are the tread, the sub-tread, the shoulder, and the sidewall. For the reinforcement, we also measure the width, which is the distance that the reinforcement is covered in the width of the tire. As we can see here, we have 5 belts, each one with a different width in the tire structure, and then another 2 sets of reinforcement along the circumference of the tire. And for the reinforcement, we measure the width, the orientation, which is the angle that the reinforcement is creating along the tire, the spacing between the steel cords, and the cross-sectional area of each of the reinforcements. And again, for the tire, the material that occupies the most volume is rubber, and we consider 2 material models, hyperelastic and hyperviscoelastic. The hyperelastic material constants were provided by the tire manufacturer, and the hyperviscoelastic characterization was performed by using a dynamic mechanic analyzer. And finally, the reinforcement was considered as linear elastic. The finite element types that we use for the tire model, they vary according to the location in the tire structure. So first, the Cartesian elements were used in the region that will be in contact with the pavement surface because they provide a more accurate prediction for the contact stresses itself. Then the cylindrical elements, they are an alternative for the Cartesian elements when you are dealing with curvilinear geometries, and they exactly represent this curvilinear geometry. So you're not sacrificing accuracy. They are computationally more expensive, but because you can cover a big radius with less amount of cylindrical elements, you are saving computational time at the end of the day. And then hybrid elements, which are used to model incompressible behavior. So rubber is a prime example of incompressible material. Some research have tried to model the incompressibility of the rubber as a linear elastic material with a Poisson's ratio close to 0.5. But that's a risky approach because you can have problems with shear locking in your mesh. And then the rebar elements, which is how you model the reinforcement in the tire without the need of using homogenization. So you can pretty much input the elastic modulus of the reinforcement or steel and the hyperelastic constants of the rubber without using homogenization. So the analysis approach is also, it depends on if you're considering the pavement as infinitely rigid or as deformable. So if it's, but for both of those, you start with the axisymmetric model. Since the tire, you can do the axisymmetric simplification. So in this stage, you introduce the cross-section geometry, the distribution of material properties, and the material characterization for each of the materials in the tire. And then if you are assuming the pavement as infinitely rigid, you can use the ALE approach, the augmented Lagrangian approach, in which the tire is not actually moving, but you're using the transport analysis to predict the response of the tire in the steady state. In this case, we can use a finer mesh in the contact between the tire and the pavement, but you can use cylindrical elements in the rest of the geometry. However, if you're modeling the pavement as a deformable body, then you cannot do that anymore because your tire is actually moving on top of the pavement. So the mesh is uniform all along the circumference of the tire. And then you cannot use cylindrical elements anymore, but you are using Cartesian elements. So this is a comparison between the two approaches. The ALE approach allows you to have a finer mesh in the contact between the tire and the pavement and have bigger elements along the circumference. But if you're using the Lagrangian approach, you have to have a uniform mesh all along the tire. For the ALE approach, you use the steady state analysis, which is less computationally intensive. Actually, you can run this analysis in a couple of hours. But if you're using the Lagrangian approach, the analysis is quasi-static. And this simple analysis just to roll the tire heel can take up to 2 days. And then once more, you can use, if you're using the LAE approach, you can use cylindrical elements. But if you are using Lagrangian approach, you're only using Cartesian elements. So now the first out of the 4 models, the hyperelastic rubber or rolling or hyperelastic tire rolling on rigid surface. We use this model for validation and to predict the 3D contact stresses at various rolling conditions. And the test metrics that we use for this modeling consider various speeds, applied loads, and tire inflation pressure. So first, for the rolling conditions. So the procedure is you have to build a plot where you change the torque applied to the tire interaxis with respect to the angular speed. And then the free rolling frequency will be the one that will provide you with 0 applied torque in the axis of the tire. So if your frequency that you're analyzing is above that, you will have a traction or acceleration. But if it's less than that, will be a braking. And we define, in order to quantify the severity of the braking or the traction, we define 2 slip ratios. 1 slip ratio for braking and 1 slip ratio for traction. So we, in addition to the speed, inflation pressure, and applied load that I described in the previous slide, we consider free rolling, 4 braking conditions, and 4 traction cases. This is showing the validation. So we compare the predicted contact area and deflection with the one that we measure in the laboratory, and we have a very good agreement for the deflection and the contact area, which is this is the mean average percentage error is 4.2 in the case of the contact area, and it's 8.5 in the case of the deflection. However, we see that the contact stresses is for the maximum vertical contact stresses is not as good. And this is where the issue with the contact between the pin and the tire becomes relevant. So not all the pins are actually measuring the actual contact stress between the tire and the pavement. So there are some accuracy issues that we are seeing here. So for some locations in the tire, the prediction is good, but for some others, mainly at the edges of the tire, is not as good. And this is just one of the results. We saw that when you're varying the rolling condition, the main effect is seen on the longitudinal contact stresses, not so much in the vertical and transverse. These plots, what it's showing is the variation of the longitudinal contact stresses along the contact length of the tire. The figure on the left-hand side is for a braking, and on the right-hand side is for traction. So the gray line is for free rolling, and as you increase the severity of the braking and the traction, the value of the contact stresses is reaching a maximum value from the rear end of the tire. And this is related to the limit that is imposed by the friction. So once the longitudinal contact stresses can increase so much, and that limit is established by the friction between the tire and the pavement. Now moving on to the hyperviscoelastic tire rolling on rigid surface. Again, this allows us to evaluate the effect of the temperature in the tire and the speed of the tire on the contact stresses and on the rolling resistance. So for the same matrix that we use the hyperviscoelastic, we added 3 values of temperature: 25, 45, and 65 C. This slide deals with the rolling resistance, which was obtained based on the static equilibrium of the tire. This T is the applied torque. Because it's a numerical procedure, you can guarantee that the torque at the axis of the tire will be equal to 0. Omega is the angular speed of the tire. V is the speed at which the tire is traveling. And Fx is the horizontal reaction in the axis of the tire. So based on this model, we concluded that the tire inflation pressure created in the diminution of the rolling resistance between 8.3 and 30%. The applied load has a linear effect on the rolling resistance, and this is backed up on the definition of coefficient of rolling resistance, which is supposed to be constant for a tire, and it's the ratio between the applied load and the reaction in the longitudinal direction. And then the effect of temperature dependent it was coupled with the other variables. So it was more relevant for certain values of tire inflation pressure and speed, but for other values of speed, the effect could be different. And the speed has it has the opposite effect than the temperature. Pretty much, for example, the speed can increase. The tire inflation pressure can increase the stiffness of the tire, but at the same time, if you have a stiffer tire but the temperature is also high, then the behavior of the rubber itself will be lower because it's a viscoelastic material. So that's why they're coupled to each other. Based on these results, we were able to propose an equation that predicts the rolling resistance for this set of values. This is just a modification of the ASTM standard to measure the rolling resistance, which it doesn't include the effect of temperature. So this K parameter with the square root of the temperature is something that we are proposing, and we see that the fit between what is predicted by the finite elements and what is predicted by this equation is very good. We also study what was the behavior of the energy in the tire components. So again, we have a set of rubber components in the tire, 4 in our case, and we wanted to see how the temperature and the speed are affecting the distribution of the internal energy in each of the tire. And the conclusion was that the subthread and the sidewall has the higher contribution to the internal energy, as we can see here by the green and red bars in the total energy of the tire. The contribution of the subthread was between 40 and 70%, and the contribution of the sidewall was between 25 and 50%, depending on the values of speed, temperature, load, and tire inflation pressure. And the effect of the speed decreased as the temperature became higher. And the applied load mainly modified the internal energy in the sidewall. This slide is comparing the effect of these variables in the three-dimensional contact stresses. And once more, we saw that the main effect was seen in the longitudinal contact stresses. So we noticed that the speed is increasing the peak value of the longitudinal contact stresses, and the value was as high as 17%. On the other hand, the temperature, since when you increase the temperature, you're decreasing the stiffness of the rubber. When you increase the temperature, the contact stresses are reduced, and that reduction could be as high as 33%. And in order to have like a global assessment of the longitudinal contact stresses, we decided to use the ratio between the root mean square error of all the contact points between the tire and the pavements and the maximum value of the longitudinal contact stresses to conclude that the highest effect was around 10.2% in this ratio, which is what this plot is showing. So the blue line is the root mean square error between the tire at the specific case and the stiffest rolling surface, and the red line is the maximum value. So the closer the blue line is to the red line, it means there's a more significant effect of the variables on the longitudinal contact stresses. And the vertical contact stresses, as we noticed in the case of the hyperelastic tire, were not affected significantly by the variables. Now moving on to the hyperelastic tire on elastic pavement. So in this case, recall that the analysis is different. So in this case, we can actually see the tire rolling on the deformable surface. For this case, as an initial step, we assume that the behavior of this body is linear elastic, but the tire is hyperelastic. So for this analysis, we fix the loading condition. We set the load to be 44.5 kilonewtons and the tire inflation pressure 758 kilopascals, and the speed was 8 miles per hour. Kilometers per hour. But the speed is not expected to have any effect on the conclusions, because first the tire is hyperelastic, which means the speed doesn't have any effect on the properties, and that is the case also for a linear elastic material. The support conditions for this deformable, which is simplifying the pavement, we did analysis for this value of load and inflation pressure on a full three-dimensional pavement model. We check and we come out with with springs that will support this deformable surface on the 3 orthogonal directions. So there are springs in this direction, which is the transfer direction, springs on this face, on the back face of the tire model, and springs at the bottom of the deformable surface. And we changed the modulus, the elastic modulus of this surface. So we consider between 100 and 100,000 megapascals for this, which is the range for asphalt concrete. Probably 100 is too low, but we wanted to go very low to see what will happen. And then probably 100,000 is too high for asphalt concrete. But considering we wanted to cover the whole range. So with respect to the stiffest case, which is an elastic modulus of 100,000 megapascals, the contact area and the deflection didn't change that much. It only changed around 3%. And it was mainly between the two lowest values of elastic modulus. And then again, using the root mean square error and the coefficient of correlation, it was noticed that the longitudinal contact stresses were the most affected. Now we were also able to see the energy dissipated by friction, and it changed between the lowest and the highest elastic modulus, 8.5%. And again, as we did is in the case of the hyperviscoelastic tire, we checked the variation of the energy in each of the internal energy in each of the components of the tire. And we noticed that the total internal energy in the tire itself did not change, but once you check the variation of each of the components, it changed around 5%. So now this is the hyperelastic tire rolling on a viscoelastic pavement. So it's pretty much the same model. The only difference is that this surface is not only deformable, but it's also linear viscoelastic. So we can change the temperature in this slab, in this deformable surface, and we can capture the effect that the speed of the tire is having on the pavement responses, or the response of the tire. Again, the support conditions for this model were obtained from the three-dimensional pavement model, and they had the same location. But in the previous case, since the material was linear elastic, we could perform a monotonic analysis. You apply the load and you do a static analysis and you get your constants. For this case, we actually perform a full 3D model with moving load, three-dimensional contact stresses, and then based on the pavement responses, we calculate the values of the constants. This model allows us to compare two approaches that has been used to predict the contribution of the pavement to the rolling resistance. One is based on the dissipation of the asphalt concrete, and the other one is based on the deflection of the pavement structure. And this is the test matrix. Since this is more computationally intensive, we decided to reduce the test matrix. Remember that each of these analyses can take up to 2 days. This is relevant for the rolling resistance. So, as I discussed, the asphalt concrete, dissipation of energy. Yes. And this is related to as I described in the introduction to fuel consumption and the use phase of the LCA for the pavement. So we took two values of load, 35 and 44 kilonewtons. So we can capture for at least two values the effect of the applied load. Two values of tire inflation pressure, one that is relatively low, 80 psi or 552 kilopascals, and 110 psi or 758 kilopascals. Two speed, one very low and one relatively high or highway speed. Two temperatures, again one very low, minus 12 C, and one very high, 45 C, and two type of pavement structures, thin and thick. The way these two pavement structures are represented in this model is with the value of the elastic support for this deformable surface. So these are the results for the rolling resistance, which was obtained based on the reaction along the traveling direction in the axis of the tire. And we noticed that the greater rolling resistance was at the highest temperature and the lowest speed, which makes sense is for this case is when the AC is the less stiff or the most compliant because of its viscoelastic behavior. And we notice also that the temperature is more relevant than speed regarding the rolling resistance. So a change in the temperature in the pavement structure is more relevant regarding the rolling resistance. I want to mention here that there is no heat exchange between the pavement and the tire. So this is only the value of temperature in the pavement structure itself. And if the pavement is very stiff, which is for the highest value of speed and the lowest value of temperature, there is no significant difference between the thick and the thin pavement, which is to compare the red and the green bars for the stiff case, which is the low temperature, T1 here and T1 here. And also, by these three bars, the green, blue, and gray, are comparing the effect of the applied load and the tire inflation pressure. And we see that it has a higher impact. So when you decrease the load, when you decrease the applied load, your rolling resistance is smaller. And when you increase the tire inflation pressure, the rolling resistance is higher. But it's affecting more to increase a change in the tire inflation pressure is more relevant for the rolling resistance than a change in the load. And then the fluid conjecture, which is pretty much to compare the two approaches I mentioned a few slides back, the one that comes from the dissipation of the asphalt concrete and the one that comes from the deflection of the pavement structure. So these two procedures, we decided to compare them in this model, and we noticed that there is no significant difference. So this first column shows the rolling resistance obtained from the dissipation of the asphalt concrete. These two columns shows the dissipation calculated based on the deflection of the pavement, considering and without considering the effect of the in-plane contact stresses. And these two show the difference. So we see that the comparison between these two, the error is less than 2% for all the cases. And when you are not considering the in-plane contact stresses, it's always less than 3%. So based on this, we concluded that first, the thin pavements have higher contribution to the rolling resistance than thick pavements, and that the in-plane contact stresses they don't affect that much this contribution to rolling resistance. So finally, I'll be talking about the semi-coupled tire pavement model, which is how to combine the tire and the pavement model in an indirect way. At the beginning, we tried to do it in a single finite element model, but we had an issue with the computational resources, because if only this model, which is way more simplified than considering a full pavement, takes 2 days, considering the full pavement model will have orders of magnitude more elements than this simplification. So it will take more than probably weeks, maybe months. So we decided to do an indirect approach, which consists of having multiple steps. Okay, so here. Okay. I'm having some issues here. Okay, so the first step is to model the tire as a hyperelastic tire rolling on deformables on a rigid surface. You obtain the contact stresses. You apply those contact stresses in a pavement model, and this pavement model is the model that we usually do in our research group, which have all the variables. So it's a linear viscoelastic asphalt concrete, stress-dependent base layer in the case of thin pavements. We have a moving load, three-dimensional contact stresses, dynamic analysis. With that, we obtain the constants to support this model, which is the hyperelastic tire on a deformable surface. And this deformable body, it's a linear viscoelastic, so you can consider the temperature, the same values of temperature that you use for this model. And once you do this analysis, you can set an extra set of contact stresses that you can apply again to the same pavement model, and then you can compare these two models to see what the effect of the deformability of the pavement surface is on the pavement responses. And this table summarizes the results that we have so far. So here is showing you the kind of pavement and the value of load and tire inflation pressure. So the upper three are all thick pavements. The one at the bottom is the thin pavement. S3 and P3 is the highest load and tire inflation pressure, which is the same applied for the thin pavement. And then only for the thick, we changed the inflation pressure to the lowest value, and we kept the inflation pressure constant, and then changed the value of the applied load. So we see that if the value of the load and the tire inflation pressure is the highest, there is no significant effect on either of the critical pavement responses. All these pavement responses are related to are critical pavement responses that MEPDG links them to specific failure criteria. So for example, for the longitudinal strain at the bottom, the AC is just 0.2%, and it goes on for the rest of the responses. I should mention here that all these results are for the most compliant case, for the most compliant pavement, meaning for the highest value of temperature in the AC and the lowest speed. So, and it's similar for the case of the thin pavement. So again, for the high value of load and inflation pressure, it doesn't have a significant effect of any of the pavement responses. However, for the other two cases, let's say for the low value of inflation pressure and high value of load, we start seeing some effect. We can see here that the shear strain in the AC, the error can be as high as 15.5%, the difference. And in the case of the vertical strain in the AC, the difference is more than 30%. The same for the other value, 10% if the value of the applied load is different, and then close to 50% in the case of the vertical strain in the AC. Even in the base, it's around 10%. So, and this is related to the way the tire is distributing the stresses in the on the pavement, depending on the load and the tire inflation pressure. In other words, when you have the high load and high inflation pressure, the distribution is different, the contact area is different, the magnitude of the stresses is different than if you're applying a lower value of tire inflation pressure, or lower value of load. And when I was comparing also the stresses between the rigid surface and the deformable surface, the main difference was not so much in the vertical contact stresses, but in the transverse contact stresses. So when you combine all these effects, you see that the difference become significant. With that, the final remarks. First, the vertical and transverse contact loads and longitudinal contact stresses are full breaking, can be represented on analytical expressions because of the variation that they have along the contact length. The vertical contact stresses were not significantly affected by speed and temperature, as long as you keep the value of tire inflation pressure and load constant. The contact area increased around 70% due to temperature and decreased 4% due to speed. The longitudinal contact stresses were the most affected during the analysis that we performed. Temperature and load were the most relevant variables affecting rolling resistance due to the tire structure. And the pavement stiffness affected the longitudinal contact stresses the most. Rolling resistance for thin pavements was higher than for thick pavements as long as the value of the applied load and tire inflation pressure is the same for the tire. And the most critical pavement response between consider or not the pavement as a deformable surface is the vertical strain in the asphalt concrete layer. And finally, the tire inflation pressure is more relevant than applied load for rolling resistance when considering viscoelastic pavement. And that's it. Thank you very much.
Thank you for a good presentation. Can you go to slide number 35?
35?
If I'm not wrong. Let's see. 34 or 5. No, before this one.
This one?
No, before this one. Go back. Yeah, this one. When you say no difference between thin and thick, you mean both are plastic, right?
Is This analysis is considering the pavement as a viscoelastic. But since you're in the low temperature, high speed, it can be considered as elastic behavior.
I know that our thin and thick models, finite elements are different, right?
Yes.
So comparing these two wouldn't be safe. I mean, because you are modeling thin pavement base layer as non-linear, right?
Mm-hmm.
And thick pavement base is linear.
Mm-hmm.
So as far as I remember, the results were not like consistent with each other. So I wouldn't directly compare thin and thick together.
Mm-hmm.
Within thin, you can compare different like assumptions or different loading case, but within thick the same. But comparing thin to thick would be a little bit tricky.
Yeah, that's accurate. But there are two things. First, the main objective is for you to check which one is, because when a truck goes, it doesn't only travel on a highway. At some point, it's gonna go on the local roads, which we model as a thin pavement. But the thing is that the important thing about this is that it's only close to each other if your temperature is low. But if your temperature is high, which is the T3 value, look that the difference is high, right? So I guess the message here was to say that, okay, the stiffness of the AC layer is very important no matter what you have underneath, right? As long as that layer is in the stiff range. We're talking about a really low temperature and a very high speed. So that's why. So the message is like, yeah, if the AC layer is stiff, you don't see that much of a difference. But if the AC layer is not stiff, there is a huge difference.
That's true, but yeah, I mean it's a little tricky because putting the red and green columns together and comparing the two, there's like 135, then I'm putting like 231.
Mm-hmm.
135, the green one is the 620.
Mm-hmm.
Comparing 20 to 35 is not consistent because you are using, I guess the red one is thin. So the thin structure functions and the layer functions different than the thicker structure.
Yeah, so which is pretty much.
You shouldn't compare those two together.
Yeah, I see your point, but the idea, because the tire is the same, the material properties of the tires are the same, the applied load is the same, the inflation pressure is the same. But so you're saying, okay, if the structure is different, this is what we're seeing. So it's kind of like, yeah, it's a.
Yeah, I don't know how much of that difference is related to the base layer assumption that you use. That's what I'm saying.
Yeah, I see you again.
The same model that you could say, okay, this 15 newtons difference between this related to the structure thickness.
Mm-hmm. No, whatever. It's because it's like if you, because we're not trying to go to the detail of each. Okay, what happened if I change the base layer to another material? You probably will get different results. But the idea here was not to provide a detailed analysis of each of the variables, but just to see in the global picture, what if you have a different pavement structure? And that's why we're seeing this result. It's not to go to the detail of the pavement structure, but to see in general, if your AC layer is stiff, what is underneath is not that important. That's the main comparison of this.
And also, for the last one, you said highest impact by reducing load.
Mm-hmm.
How did you compare high pressure?
Yeah, that's a good question too. Because so the what I was trying to convey there is like we have a base, like let's say a base value of high tire inflation pressure and high load, right? So what happens if you change one at a time? So let's say I'm gonna keep for the blue line, I'm gonna keep the inflation pressure the same, the high value, but I'm gonna change the load. So you see that is the difference is not much. Which we like, as you know that if you reduce the load, your rolling resistance will be smaller. Okay, but what happens if you now keep the load the same, but you reduce the tire inflation pressure? So the message here was to say like, okay, look that the difference is higher if I change the inflation pressure, the the load, yeah, you see some effect. But if you change the inflation pressure, the difference is high. They have opposite effect, right? One is reducing, one is increasing.
My point is that when you say change, you cannot compare tire pressure change. How much?
Yeah.
Change or talking about one unit change of load is different than one unit change of tire pressure. So you need to kind of normalize and then talk about it.
Yeah.
I wouldn't actually agree with that point just because of that change there that you can see the curve on the bar. Because you haven't normalized it, you don't know. And at the end of the day, one unit change of tire pressure is not the same.
Yeah, that's.
Each load you use there would be different. You go from 5 trips to 18 trips would be very different than going tire pressure on the.
Yeah, that's a very good point again. But if you see these values, that is what you normally will encounter in the track. If you go and check the apply load by a track to a pavement, you're not gonna see a value of 5 kips. You're gonna see between 35 and 44. 44 being on the high end, 35 being which is the train, like the tracks tend to be overload, not underload. And so 35 is in the normal range, 44 is on the high range of the apply load. And the same for the inflation pressure. It's between 80 and 110 psi. 110 psi being on the high end, 80 psi being on the lower end. I thought, and what you said is true. Like you're saying this, but how you're comparing this percentage change, but how much are you changing each of the two variables? And actually, I did the math, and it's similar, but without needing to go to the detail of the data analysis, just to see like the general picture of what will happen in real life. This is kind of like what we're seeing, that the inflation pressure has more effect on the rolling resistance than the load. Of course, I understand what you're saying. Like, I mean, but you change, how much did you change? You didn't change that much, this value. What if you change it more? Of course, this guy is gonna go below here. So are you gonna say the same thing? No. So I agree with you. Maybe this has to have a complement disclaimer here where I'd say, okay, for this range of values, which are the ones that are seen in the field most of the time.
Well, just to follow up on that, I kind of agree actually that some of the conclusions or findings, the way you summarize, you bring those out based on your results and analysis and modeling results. I think this is a well-known topic, especially there was a huge amount of work done way back in the 60s, 70s. Okay, well, primarily on unpaved roads, how couples go wide, right? Mobility studies back then. And actually, Army Corps of Engineers, which they just say the mobility, which is focusing on that one set. For airport pavements, like Henderson Air Force Base, Dayton, Ohio, they did a lot of studies, a lot of empirical equations. Actually, those empirical equations eventually made it to the Survey Stability Manual, and that's how IDOT adopted some of those things. Did you have a chance to go back and look at some of those? How they did all the empirical studies to derive all of the rolling equations?
No.
Well, I really suggest you do that. I covered that in small block and transportation source. And here are the big things that make a huge impact on our life. First of all, everything they did in those studies, they looked at the hard surface tire imprint, the contact surface. You're hitting on those topics here with the layer. You get a lot more surface area, contact area, right? As opposed to softer and less they relate to the inflation pressure. So that's how they base everything on that. Friction, of course, obviously has a huge impact on the rim pull, the rolling rim pull versus rolling resistance, and what's really driving the car. And the other big thing is, if you look at it everywhere, rolling resistance is a function of big times. Well, that's what we call a sink, right? The unprepared ground is sinking out big time. In your case, it is not sinking, but let's take that as deflection here. And deflection, I think, in my opinion, is the one maybe that should come into the formula and changing according to the asphalt temperature, the stiffness, and everything. So that's the angle, if you look at the empirical studies and how they wrote those things, those factors, important factors contributing to those, the way you can actually look at your results in a way. Because I'm not sure if you're ever considering how much deflection, viscoelastic, whatever, how much deflection is contributing to all of your resistance.
Yes. So the thing is that maybe I didn't do a good job explaining that, but the main thing is like no study so far has looked at this with the grade of detail that we're considering the tire.
I totally agree. I mean, this
And
is an amazing type of modeling that you're doing, but some basic concepts that you can actually go visit from the institutional knowledge and bring them into your study from an interpretation point of view of your results, saying that, see, these were the most important contributing factor that documented back then. And they kind of, you can use those to justify some of the results too.
Yeah, so that was the next part of the answer is like we actually, because now our group is growing big on rolling resistance, and we kind of like have some of us, each one focusing on a different thing. And we have seen that it's expected that each of us would overlap with each other, and that was kind of the idea of the use phase and rolling resistance, and see each of the effects of the of the pavement parameters on the rolling resistance. So now with the deflection thing, there are these flange. Did I say it right, Miriam? Flange conjecture. Flange conjecture is pretty much that. It's like there are two approaches to calculate rolling resistance. One is based on the deflection, which I didn't want to include the slide here because it's have some mathematical procedure in it. But pretty much it's for the deflection, you are calculating the external work of the forces that you're applying on the pavement. So if the deformation of the pavement is high, you're gonna see that reflected in that approach, which is the deflection approach. These two columns here.
Right. If there's been some sinking that now the heel has to come out of that.
Yes. So that method will capture that. So there's another method, like if you have a viscoelastic pavement, forget about the tire, the pavement is also gonna have some kind of contribution to this dissipation. And what this slide is showing, which is kind of like we didn't have the chance to do before, is because it has been proven mathematically. There is a formal mathematical expression to prove that if you calculate the contribution of the pavement to rolling resistance based on the dissipation of the AC, that's one procedure. But if you focus exclusively on the deflection, that's another procedure. And what this slide is showing and what these authors prove mathematically is that they're the same. And that's what we're getting here. That they're pretty much the same. But this is based on the simplified pavement. We need still to move on to the full pavement. So the short answer will be like, yes, we're considering the deflection, and we check what the relationship is between how the surface of the pavement is deforming and how much that pavement is contributing to the rolling resistance. Any other question? Okay. Which one?
Your second point that based on RMSE and R-square, particular context versus the most effective. How could you get this conclusion out of RMSE and R-square?
Actually, we discussed this. Remember because you were the one that helped me with this. I remember because pretty much I have a tire which is has the same mesh, and is contacting the surface. So the mesh has a set of nodes. So a set of nodes is contacting the surface. Either it's rigid or it's flexible, it's whatever. So I wanted to come up with a method that kind of like can see at the whole set of points in comparing the effect, how it's changing. So I remember your advice being, you cannot focus on only one. you cannot focus only on RMSE because, or exclusively on R squared, because you can get misguided, because a high R squared doesn't mean you have a good approximation, because the points can be equally spaced from the equality line. So that's why you also need to the RMSE. So that's why I decided to go with that approach based on your advice, and that's how I build this plot. So this is the maximum value, and this is the RMSE, because it has actually, this is not a good light to answer that question. I didn't include it here, but pretty much I have a set of plots where I'm comparing the calculated with the two methods, equality line, and R squared for that, the cloud of points, and the RMSE. And checking both of them, I came up with the like, that was the criteria of those two together, seen for like, will give me how much the contact stresses were changing.
Those two will give you how accurate you are, not how much you affected.
Yes. Yeah, and
that's my question. How do you get how much it affected the longitudinal stress, how much affected out of these two? You can get your accuracy out of these two, just how much they compare to the original, to the actual, to the predicted, or whatever. But you cannot get how much it affected these two.
Yeah. So when you say accurate, you have something as a reference, right? So you say, okay, I'm expecting this, so I'm seeing how much accurate. So that's what I did. I said, like, okay, my stiffest case, which let's say it's in the deformable case, my stiffest case, which is the highest speed with the lowest temperature, will give me the stiffest, and I'm gonna take that as a reference. So if I check the R squared and RMSE compared to this guy, I can see how much they're changing. How much they're changing with respect to the steepest. And I agree with you, that will give me kind of how far from the accurate, and I'm assuming that the accurate, the accurate the steepest. And actually when we wrote the paper, we put that disclaimer. This kind of information is not commonly used to check the effect of variables in a problem, but if you take, I'm saying I'm gonna take this one as the accurate, just to see how much it's changing with respect to that. Because the risk with taking one value, if you take the maximum, that's just giving you the comparison on one specific point. How do you know what's happening in the rest? So that's why we decided to do this with the RMSE and the R squared, based on the stiffest case being the most accurate.
Can we take a look at it later?
Yes, of course, anytime. I think that's it.
That's it? All right, no other questions? Thank you very much, Jaime.